Hello dear friends, welcome to a lecture on ring theory. In this lecture, we shall study units in a ring. I have written here definition, we shall see the definition, examples, a result as a lemma and some problems we shall solve. I have written definition here as let R be a commutative ring with unit element. It is a commutative ring with unit element and element A belongs to R is a unit in R if there exists an element B belongs to R such that A into B is equal to 1, where 1 is the unit element. Now you see we have the unit element in a ring generally denoted by 1, and we know the definition for unit element. 1 is unit if A into 1 is equal to 1 into A is equal to A for all A belongs to R, then 1 is the unit element. So here unit element is 1, but we have defined unit, and element A belongs to R is a unit in R if there exists another element or maybe the same element. There exists an element B belongs to R such that AB is equal to 1. Now A into B is equal to 1 means actually A and B are multiplicative inverses of each other. This is the definition for multiplicative inverse. We have A into B is equal to B into A. It is a commutative ring and is equal to 1. Then A and B are inverses of each other, multiplicative inverses of each other, and that means if an element in R is a unit if it has multiplicative inverse, that means A and B both are unit in R. So every element which has multiplicative inverse is a unit in a ring. And see, there is difference in the unit element and unit. The unit element is unique, means only one, and that is denoted by 1. But every element which has multiplicative inverse is a unit. So therefore these are different. Unit element and unit are different. Every unit element is a unit. Now 1 is a unit element. 1 is unit element. 1 is also unit in ring, because we have 1 into 1 is equal to 1. So therefore 1 has multiplicative inverse itself, and therefore 1 is unit. So unit element, every unit element is unit, but unit may not be unit element. So that is difference in unit element and unit. Unit element is only 1 and unit are those elements which has multiplicative inverse. Some examples. First is the example in the ring of integers denoted by Z, addition and multiplication. 1 is the unit element that we know, and while there are only 2 units in the ring of integers, and which are 1 and minus 1, because these are the only elements which has multiplicative inverse in this ring, 1 and minus 1. Other elements do not have multiplicative inverse, because if you consider 4, then its multiplicative inverse is 1 by 4, which is not in integer, and thus in the ring of integers there are only 2 units, 1 and minus 1, and in these rings, that is ring of rational numbers with usual addition and multiplication, ring of real numbers, ring of complex numbers, every non-zero element is a unit. Or in other words, in any field, every non-zero element is a unit, because by definition of field is the ring with commutative ring with unit element in which every non-zero element has multiplicative inverse. So therefore field has every non-zero element in a field is a unit. And if you consider this finite ring addition modulo 4, Z4, which contains these 4 elements 0, 1, 2, 3. With addition modulo 4, multiplication modulo 4, the units are 1 and 3. 1 is the unit element, but 1 and 3 are units, because we have, see, 1, the multiplicative inverse exists for 1 and 3. We have 1 into 1 for this example third. 1 into 1 is equal to 1, therefore 1 is unit, multiplicative inverse of 1 is 1. And also the multiplicative inverse of 3 is 3, because 3 into 3, this is multiplication modulo 4, and that is 3 into 3 9, 9 divided by 4 gives remainder 1, and therefore 3 into 3 is 1 under multiplication modulo 4. The definition is that A multiplication modulo 4 denoted by this notation or this notation is the remainder when AB divided A into B, usual product, is divided by 4. Here 9 divided by 4 gives remainder 1, and therefore the inverse of 1 is 1, inverse of 3 is, multiplicative inverse of 3 is also 1, and thus 1 and 3 are units in this ring. So these are some examples of units in a ring. Now we shall prove this lemma. Let R be a Euclidean ring and A, B are two elements in R. If B is not equal to 0, B not equal to 0, non-zero element is not a unit in R, then D value of A is strictly less than D value of AB. We have defined earlier what is the meaning of Euclidean ring. Euclidean ring, the definition, it has two conditions. R is a Euclidean ring if for element A, B belongs to R, non-zero elements, R is Euclidean ring. There are two conditions for Euclidean ring. First is non-zero element A, B belongs to R, D value of A is less than or equal to D value of AB. What is D value? D function is Euclidean function which has non-negative integer. The value of here D of A is a non-negative integer. Non-negative integer, and we have D value of A is less than or equal to D value of AB. That is the first condition in Euclidean ring. And the second is of division algorithm. Here we are going to use only the first condition of Euclidean ring. And second was second is AB are elements in R. There exist another elements Q and R belongs to R such that this A is written as QB plus R, and where the D value of R, this is remainder, D value of R is 0 or D value of R is less than D value of B. So this is the definition of Euclidean ring that we have studied in our earlier lectures. You may refer that, and we are going to use the first condition to prove this lemma. Usually D value of A is less than or equal to D value of A into another element, that is AB. But here this equality possibility is discarded and only we get D value of A is strictly less than D value of AB when if B is not unit. If B is not unit, then D value of A is strictly less than D value of AB. So to prove this, we shall consider an ideal of R, and we shall denote that ideal by A. So we shall write the proof as taking an ideal. Consider an ideal A of R, where the ideal A is generated by A, and ideal A generated by A means every element of this ideal is multiple of A, and that is written as ideal A generated by A. This is the symbol we denote, and it is generated by A, and means every element is multiple of A, x into A. X belongs to R. This is an ideal of R. Now we have by first condition of Euclidean ring. First condition of Euclidean ring. D value of A and D value of x into A. What is the first condition we have written? D value of A is less than or equal to D value of A into any other element, and therefore this is less than or equal to D value of x. For this x is not equal to 0 in R, and this means D value of A is the minimum in regard to D value of any element in A. So this is any element in A, and this is element A which generates A. Therefore, the D value of A is the minimum than D value of any element in A. Now, AB belongs to A. AB belongs to A, the element where B is element in R. Take any element B in R, then this will be AB will be multiple of A, and by the definition this XA, here X is taken as B, AB belongs to A. Now if what is the general result we have, then D value of A is less than or equal to D value of AB. See, now but if these are equal, this is the usual result, but what we want to prove, it is strictly less than. So what happens if these are equal? If D value of AB is equal to D value of A, then D value of AB becomes minimum, because we have written D value of A is minimum. So therefore D value of AB is also minimum with regard to this ideal A. Then the D value of AB is minimum in ideal A. And if D value of AB is minimum, then as like A, every element of A, ideal A is a multiple of AB. Therefore, every element of A is a multiple of AB. If we assume this, then every element of A will also be a multiple of AB. Now in particular, A is an element in A. A belongs to A. So therefore A is also a multiple of AB. A is some multiple, or A is a multiple of AB. And because A is multiple of AB, we can write like this: A is equal to AB into some element, and that element we may consider as X. Therefore, we can write A is a multiple of AB, means A is equal to AB into X for some X belongs to R. Now you see this equation here, A is equal to AB into X, and A is common on both sides, and this R is Euclidean ring, it is integral domain, and in integral domain cancellation law holds. and therefore this a can be cancelled from both sides, and what we get is 1 is equal to bx. So we can write the reason for this. R is integral domain. R is an integral domain because Euclidean ring is integral domain. By cancellation law, we get, see, a cancels, we get 1 is equal to bx. And what this implies, 1 is equal to bx. See this definition. If AB is equal to 1, then A and B are unit. So therefore here 1 is equal to bx, then this shows B is a unit. So B is a unit, and now you see it is a contradiction because B is not a unit, that is given. This shows that B is a unit, and this is a contradiction. Since it is given that in the theorem by hypothesis, it is given that, or in the result, in the lemma, it is given that B is not a unit. It is given that B is not a unit, and thus we have got a contradiction. And why this contradiction has arrived? Because we have supposed this d of AB is equal to d of A, and this is wrong. Means we here equality is discarded. D of A is not equal to d of AB. Means what remains? D of A is strictly less than d of AB. So therefore d of A or d of AB is equal to d of A. Our supposition is wrong, and thus we must have this is greater than d of A, we must have, or d of A is strictly less than d of AB. Equality possibility is discarded, and this proves the lemma. So thus we have proved lemma if B is not a unit. Now see, simple example can be considered as of a ring of integers, which is Euclidean ring, and there we define the Euclidean function d function as the absolute value. So in this ring, in Z addition and multiplication, we define d value of A is equal to absolute value of A, and then what we have is d value of AB is equal to absolute value of AB, which may also be written as absolute value of A into absolute value of B. And we have the relation as this absolute value of A if B is not unit, means B is not equal to plus or minus 1. In the ring of integers, we know 1 and minus 1 are units. If B is not equal to plus minus 1, then obviously mod B will be greater than 1, and therefore we have absolute value of A is strictly less than absolute value of A into absolute value of B, because this value is greater than 1. So this side becomes greater, and that is d value of A is strictly less than d value of AB. This is d value of AB. So that is the example related to the ring of integers. Now we shall consider some problems. For first problem we shall consider is the necessary and sufficient condition for A to be unit. the necessary and sufficient condition, let R be a Euclidean ring. A necessary and sufficient condition for an element A belongs to R to be a unit in R is that d value of A is equal to d value of 1. 1 is the unit element. So this is necessary and sufficient condition. A is unit if and only if d value of d value of A is equal to d value of 1. That is the meaning of this problem. And now we shall prove it. There are two parts. First is, we suppose R is Euclidean ring, and then we shall show, and A is unit in R, then we shall show d value of A is equal to d value of 1. That is the result we shall show. Let proof. The first part we shall see is, let A belongs to R be a unit in R. And because A is a unit in R, by definition of unit, A is unit, there exists an element B such that A into B is equal to 1. Therefore, there exists an element B, there exists B belongs to R such that AB equal to 1. And because AB equal to 1, we have, this implies d value of AB is equal to d value of 1. But see, we have d value of AB and d value of 1. The relation in these two can be considered. We have equality. D value of A. Now we can write this as d value of A and d value of A into 1. So what is relation between this is, d value of A is less than or equal to d value of AB. See, general relation is, we have like this, d value of A is less than or equal to d value of AB. First condition of Euclidean ring. And but what is d value of AB? This is d value of 1. So we have d value of A is less than or equal to d value of 1. And again, see, d value of 1 can be written as, so we further have to show d value of 1 is also less than or equal to d value of A. 1. Now we can write d value of 1 as d value of 1 into A is less than or equal to A into 1, you see. Now what is the relation between this? Again less than or equal to. D value of A is less than or equal to d value of A into any element. Same relation we are using here. Here we have written B as 1. And this means d value of A. Or that means d value of 1. D value of 1 is less than or equal to d value of A. Now what these together implies, d value of a is less than or equal to d value of 1, and d value of 1 is also less than or equal to d value of a. They both are less than or equal to each other, means they must be equal. Thus d value of a is equal to d value of 1. So that means the first condition is proved. Assuming R to be Euclidean ring and A is unit element, we have proved d value of A is equal to d value of 1. Now next we shall consider the converse part, and here we shall assume d value of A and d value of 1 are equal, and we shall prove R is Euclidean ring. A is unit, that we shall prove. Second, conversely, suppose d value of A is equal to d value of 1, where A is unit in R. Now here we will apply the second condition of Euclidean ring in the definition of Euclidean ring. Second condition is of division algorithm, and by second condition of Euclidean ring there exist two other elements, quotient and remainder. By the second condition, of Euclidean ring, for we take two elements and another two elements related to that. For Euclidean ring, second condition, for 1A belongs to R, there exist Q comma R belongs to R such that this 1 is written as QA plus R. This is division algorithm, and the condition is 1 is equal to this 1 is divided by A, Q is the quotient, R is the remainder, where condition for R is where d of R is equal to 0 or d value of R is strictly less than d value of A. This is the condition. Now what happens if d value of R is less than d value of A? What is d value of A? We have, see the assumption, d value of A is equal to d value of 1. But now here, but d value of R less than d value of 1 is not possible. How? Since we have d value of 1 is can be written as d value of R into 1, and we know the relation between this is less than or equal to d value of A is less than or equal to d value of A into any other element, or 1 into R or into 1, it is commutative, and this is equal to d value of R. So that means d value of 1 is less than or equal to d value of R. This is actually the relation, but here d value of R is strictly less than d value of 1, and therefore it is not possible. So thus we must have, see, this is not possible, and therefore we must have d of R is equal to 0. And that is R is equal to 0 or d value of R is equal to 0. Or R is 0, and R is 0 means what? 1 is equal to QA. So actually the condition here is, second condition is r is 0, not d value of r is 0 or d value of r is less than d value of a, and thus this second condition is discarded, means r must be 0. We must have r is equal to 0, and if r is equal to 0, you see the relation becomes, and therefore we get 1 is equal to q into a, r is 0, and 1 is equal to q into a means what? A is unit, because AB is equal to 1 means A is unit, and this implies A is a unit. A is a unit in R. So thus this is the necessary and sufficient condition for a unit. A is a unit if d value of A is equal to d value of 1. So this is a problem that we have seen for unit. There is another example where we have, if U is an ideal of a ring and U contains a unit of R, then U is equal to R. That is a second problem. If U is an ideal of a Euclidean ring R, U is an ideal of a ring R, and U contains a unit. Unit of R, then U is equal to R. Actually, we have proved this type of result in ideals. If the unit element belongs to ideal, then the ideal is equal to the whole ring, and instead of unit element, here it is unit. So the proof is simple, or solution is simple for this. Let A be a unit in R. Let U be ideal and of ring R, and A is a unit. Let A be a unit in R. Unit in R, and A belongs to U. U contains unit. We have supposed A is the unit in R, and that A belongs to U. So by definition of unit, there exists B belongs to R such that AB is equal to 1. Therefore, there is an element B, or B belongs to R, such that AB is equal to R, AB is equal to 1. The same definition we have used here, and this implies, see, D value of AB is equal to D value of 1. Now what we will have to show is U is equal to R, and thus D value of AB is not that is D value of 1, or which is equal to 1. And see, we now consider the relation. U is ideal, so therefore U is subset of R. And see, this AB is equal to, or we shall use like this. There is an element B such that AB is equal to 1, and because A is element also, you see, also A belongs to U, B belongs to R, and by definition of ideal, this product AB belongs to U, and the product AB belongs to U, but what is AB? AB is 1, and therefore 1 belongs to U. This result we shall have. 1 is unit element and that belongs to the ideal, and this directly gives if 1 belongs to ideal, then the ideal is equal to ring. So because U is subset of R, and also further if X belongs to R, 1 belongs to U, here we have, then their product, this implies X into 1, which is X, belongs to U. By definition of ideal, if X is any element in R and any element in U, their product is also in U. So the product is in U and X belongs to U. X belongs to R implies X belongs to U means R is subset of U, and U is subset of R is subset of U, means R is equal to U, and thus U is equal to R. So therefore this is proved. U is ideal and U contains unit of R, then ideal and the ring both are equal. So thus we have studied what is unit in a ring, some examples and a result, and some problems we have studied in for related to units in a ring. I hope you can understand this. Thank you for watching the lecture.